Module 3, Probability. Welcome to the world of probability, where we unravel the mysteries of chance and learn the language of uncertainty. Through examples, we'll journey from the foundational concepts to the intricate nuances of probability. Sample spaces and simple events, the ABCs of probability. Every probability experiment starts with a sample space, which is the set of all possible outcomes. For instance, when rolling a 6-sided die, our sample space is 1, 2, 3, 4, 5, and 6. Within this sample space, each outcome, like rolling a 3, is called a simple event. For a game where you roll 2 6-sided dice, the sample space consists of pairs, 1, 1, 1, 2, etc., all the way up to 6, 6. Within this, rolling a total of 7 consists of each of the simple events, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So, the odds of rolling a 7 are 6 in 36, or 1 out of 6. The fundamental counting principle. When faced with multiple choices, the fundamental counting principle gives us a nifty way to determine the total number of outcomes. Imagine you have 3 shirts and 4 pants. How many outfits can you create? Using this principle, you'd have 3 times 4, which is 12 different combinations. Now consider choosing an outfit with 4 shirts, 3 pants, 5 shoes, and 2 hats. The total outfit combinations? It's a whopping 4 times 3, times 5 times 2, which equals 120. The many faces of probability: classical, empirical, and subjective. Classical probability. Think of flipping a fair coin. Without any prior knowledge, you'd say the chance of getting a heads is 0.5 or 50% purely based on logic and reasoning. This is classical probability in action. Empirical probability. Over the past month, you observed it rained 5 out of 30 days. Thus, the empirical probability of raining on any given day, based on this data, is 5 out of 30, or 1/6. In a standard deck of 52 cards, the probability of drawing an ace is 4 out of 52, or 1/13. This is deduced purely from the structure of the deck. Say you've noted the outcomes of 100 dice rolls. If 5 appeared 17 times, the empirical probability of rolling a 5 becomes 17 1/100ths. Subjective probability. This is based on personal judgment. If someone believes there's a 70% chance their favorite team will win, despite statistical evidence, this is a subjective probability. Complements and conditional probabilities. The complement of an event represents all outcomes that are not the event in question. If there's a 20% chance of rain tomorrow, the event. There's an 80% chance it won't rain, the complement. Now, conditional probabilities come into play when one event depends on another. If 4 out of 10 students play football and 3 out of those 4 also play basketball, the probability that a student plays basketball given they play football is 3 out of 4. In a bag of 8 marbles, 5 are blue and 3 are green. If you pick a green one, the complementary event is picking a blue one. For conditional probabilities, if 2 of the green marbles have a special mark, the probability of picking a marked marble with a special mark, given that you pick a green on, is 2/3. Tree diagrams, visualizing choices and chances. A tree diagram is a handy visual tool that maps out outcomes and their probabilities. When picking a ball from a bag containing 3 reds and 2 blues, then replacing it and picking again, a tree diagram would branch out, showing all combinations of choices. Imagine you have a box with 2 gold coins and 3 silver coins. Drawing a coin, noting its type, and drawing again, a tree diagram would trace this journey. For instance, starting with a gold coin and then drawing a silver one would be one branch of this tree. Independent versus dependent events. 2 events are independent if the outcome of one doesn't affect the other. Flipping a coin and rolling a die are independent. The coin's outcome doesn't impact the die. But if you remove a card from a deck and don't replace it, the next card's probability is now dependent on the first event. If you draw an ace and don't replace it, the next draw is dependent on the first. The chance of drawing a second ace is 3 out of 51, since there are only 3 aces left in the deck. If the first card wasn't an ace, the chance changes to 4 out of 51, since there are still 4 aces left in the deck. The multiplication rule, sequencing events. This rule helps determine the probability of 2 events occurring in sequence. If there's a 1 out of 10 chance you'll oversleep tomorrow and a 1 in 5 chance you'll miss the bus, then the probability of both occurring consecutively is 1/10 times 1/5, or 1 in 50. Imagine a scenario where there's a 1 in 5 chance you'll forget your keys at home, and if you do, there's a 2 in 3 chance you'll be late for work. The combined probability of both events? It's 1/5 times 2/3, or 2 out of 15. In the next module, we will learn how to create and use probability distributions and segue from probability into statistical concepts that will set us up for our later foray into standard deviations and hypothesis testing.